So, hello everybody. My name is Vasileios Lampridis, and I work at Donzo. We are a company that does energy analytics, works with utility companies, and we provide analytics to the end consumer to have better understanding of their energy usage. Just to get an understanding of what we do, a tech stack is AWS, Spark, Cassandra, Kafka, so usual ETL and then analytics on top of that. And obviously Scala. And yeah, I forgot to mention the title of my talk, my first talk, that's why. Polymorphism for immutable objects, and straight on to why should you care. I believe that having a well-designed domain model is at the core of a well-maintainable code base. And it can help a lot in deduplicating code without losing type safety and even promoting type safety, which, if you think about it, has a very nice effect of it's almost writing tests that are used by the end user of the code instead of just being run on your version of the code. So it's very good, especially for domain models that are used across code bases. And I chose to use an example that is very similar to what we actually do on our own code base and domain, which is we model quantities, and that is, I've just picked 3 of them, energy, power, and time, and they have some nice, interesting relationship between them. You can see them there. I guess from physics you might remember them. And I don't bother at all with units, just plain numbers behind the types. And let's see how we can teach these relationships to the compiler and how we can create a nice domain model out of that. And I just tried and do a first motivating example of how ugly it would look if we were using something less powerful. And it is ugly. And I don't expect to look through much of the code. I'm just showing that, mutating stuff, and if you want to multiply, you by default throw an exception and only override because you cannot get the compiler to know what is the correct type combination. Yeah. And just an interesting note is, if you mutate stuff, you're allowed to know the concrete type even though you operate on the abstract type, on the abstract level. So you upcast something, but because you mutate, you still have access to the concrete type. And we can see now how we can retain that sort of advantage of good old mutable programming onto the immutable goodness and get even more advantages. So I skip through that. This is now the meat of the talk. So the key idea behind what we call F-bounded polymorphism is that we want to express code on an abstract level, so on the supertype, to avoid duplication, but we don't want to obviously mutate, and we need to return the concrete subtype of an operation that updates something instead of returning just the supertype. So in order to achieve that, we obviously need the supertype to have some sort of knowledge of the subtype that is actually implementing that supertype, and that starts getting messy, so let me explain. And I do a stepwise approach to arrive naturally at what is the proper solution for that. So the first attempt you'd say is, okay, let's have a type parameter on what we would like to be the abstract trait for all our quantities. And we say it's just an A that is constrained to be a quantity. And because it's immutable, we just need some method to create new instances that return that concrete subtype. And you can see that, for example, when we have a concrete quantity, we extend it to be a quantity of that energy. So we use the type on the definition of the class. So that's the first important step in F-bounded polymorphism. And that, you can see, already allows us to gain something quite nice. We can define an abstract method, so again, deduplicating code, that allows us to do something very simple, which is to sum a quantity to itself. But you can see that when I apply the concrete energy onto that abstracted method, I get back the correct type, and that is the major win already. But if I were to use the below method, I would run into trouble, and I have the compiler error message there for you. And that is because once we do the first summation, the type we get back is an A of quantity of underscore really, of undefined in a sense. But we would like to be properly a quantity of A. And that's exactly what the compiler says, that you provide something else that instead of what I would expect. So it almost leads naturally to what the solution is for that we fully now constrain quantity to be this recursive thing that it is parameterized to be an A that is a quantity of A. And that is the trick, and I'm going to explain further down. The rest remains exactly the same, and even the definition of energy remains the same. And now we can define the method that was previously failing correctly. And let us see why. And by the way, I even provide the input to be A, not even quantity of A like I used before. And this works because it is a bit tricky to truly understand, but you can see that you constrain the type A to be a quantity of type A. So when you update the object, you get back something that is again of type A that is constrained to be a quantity of type A all the way down. So that's exactly the trick that allows us to maintain immutability while having access to the concrete subtype as if we were mutating. Yeah. And just to completely tie the knot, I'm giving an example here of potential mistake you can get. For example, I just copy-pasted the definition of energy and just renamed it to power, but the rest of the types, by mistake, remain energy, and the compiler does not complain, so you can try and sum two instances of power and get back energy, which is obviously undesirable, and that's very easy to fix, actually. If you, on the same trait we saw before, if you annotate it to be a self of A, you have that self-type annotation. You can see now further below what the compiler would say if I tried to define mistakenly the power to be a quantity of energy. It would say that the self-type does not conform to the expected one, essentially. So we now have completely sort of tied the knot that we have all the type information, and also it's quite hard to make a wrong definition. Yeah, and that is pretty much the story of on the first part of the talk, which is F-bounded polymorphism. Any questions on that side before I move on to the next? Cool. So the next one. It's called functional dependency. You also, in the nice blog that Anna saw before, Lee Howey's blog, he mentions it as type deriving or type driving actually implicits. Yeah, we arrived again in implicits, sorry. And I'm going to use it as a solution to show how we can encode these relationships I showed at the very beginning, which up to now, and even if we use F-bounded polymorphism, we would still be forced to have some sort of type unsafety. And let's see. So the key idea is that effectively, if we were to express the multiplication or division, like I said before, on the abstract quantity and not having to implement it on each concrete quantity, we would need to have some way to drive the output type based on the input type. So if I have time and multiply it with power, I'm expecting to get back energy, but only if I multiply it with time. If I was to multiply it with something else, I would expect something different, or a compiler error. So that's exactly the idea that get into, that we need some way, some other mechanism to provide us the output type. And essentially, you see that would be the signature of the method, and I'm still building upon the previous self-bounded example. And I'm saying that I have the multiplier method on the quantity. So I'm having a quantity A, and I tend to multiply it with another quantity B, and I'm expecting some third quantity C. And you can see that that type C is not constrained by anything, so naturally the compiler has no way till now to know what that C could ever be. And similarly for division. And just what would be the end goal? You can see that nice thing that you can multiply one with the other and the reverse of it and add something in that, and all that nice chain of operations that naturally resolve themselves to the correct types without having any explicit type annotation. And I'm going to show you how. That's a bit chunky code, but let's ignore that because that's just the definition of the 3 units. Let's focus on these two. And let's ignore even that because it's fairly similar and focus just on the multiplication. And you see I'm requiring now an implicit that I just go multiply, but the essence of it is the types of it. So it's a thing that has 3 type parameters. And you can see that we effectively already know the first two. We know we are in the class that has type A, and we're providing another one that has type B, so we already know A and B. But we don't know C. And that's exactly where this implicit comes into play. That we say to the compiler, go please and find me some instance of multiply that is specifically created with this very specific A that I know and this specific B that I know. And if you find only one with these 2 types, then return me that instance that also carries along that type C. So I now know the type C. That's pretty much the story. And as long as that is unique, the compiler can find you that unique type, and therefore you have access to that type C. Oh, I had moved that to make the code less chunky, but forgot to delete that. So you've already seen that. So these are the 2 definitions of the 2 implicits that I showed you just before. And I think it's worth just going back because I rushed it a bit. So we have for multiply, we require an implicit multiply, and for division, we require an implicit divide, but they're very symmetric, I would say. And then we essentially use an apply method that we expect on that object with inputs this class itself, which we know is of type A because of the self-type annotation, and the other which we know is of type B. So we expect to find an apply method with taking A and B and producing C. And that's exactly what we're going to see. So we have a trait with that apply method with taking A and B and producing C. And I also follow this constraint of quantities, but this is not strictly needed for the example. But I think it's a good practice since you have that type constraint. You may as well apply it. Otherwise, why you went through the trouble? And I define two instances. So I define the first relationship of multiplicative relationship, which is if we multiply power with time, we get back energy. And I don't bother with units, as I said, just multiply the raw values of it. And if you wonder what the syntax is, using the single abstract method, that you can just define a function and Scala understand it as an implicit of that single function, and a trait of that single function, or class of that single function. And you can see that we can even do some interesting things to reduce the explicit definition. We can have, given that we know that multiplication is symmetric, we can define the symmetric power class for every such definition. So we have this implicit definition that requires these three parameters, and say, if I have an instance of the multiply that takes A, B, and C, I can definitely have the symmetric of it, which is a multiply of B and A, B times A, that gives back the same C. And you see that it takes B and A. This is a bit nasty, the naming, but it doesn't really matter. And yeah, that's pretty much it. And for division, the story is fairly similar. It's the same really pattern, just for instead of multiplying, it's dividing. And given just these three definitions, these three implicits, the compiler manages to do what is to me fairly impressive, that you can define this expression, and it does work out for you that power times time results in energy, so that you can then add the time times power that is driven by this symmetric definition, and then just add energy based on the plain addition function that is based on the f-bounded polymorphism. And then again, chain other operations. That's not the essence of it, but you can see that you can have full control of your types without needing to annotate anything. And even more, what this allows you is to even control your acceptable combination of types. So it's not inherently illegal, if you'd like, to divide power with time in the domain of physics. But in your specific domain, you just don't want it. So effectively, by not defining an instance that expresses this relationship, you get a compiler message back, a compiler error back. So that nicely allows you to express precisely the combinations you care about and disallow things you don't want to bother with. Yeah, these are pretty much the two concepts. So if you find yourself needing to construct object hierarchies, f-bounded is your way to go. And if you need to express type relationships and have something as output based on other inputs, then you should be looking to use functional dependency. And just as a bonus point, I guess, you find these exact patterns that I talked in this more constrained domain. If you open your IntelliJ and just search for map-like in the collection of Scala, or the famous or infamous, I guess, Campbell from is also exactly following this functional dependency pattern. So that's it.